All right, everybody. So you guys have about 5 or 6 minutes to work through these problems, and then we will get started. All right, let's get started. So for this first one here, we have 2 double bonds, which means we are going to be making a 4-membered ring. When we do our cyclization, so these electrons can move up to close a ring, these ones can get pushed down, we'll end up with something that looks like this with our 2 other substituents. So to solve how those are going to look, we need to take a look at our orbitals. So let's redraw this. We are using heat here, so our pattern should be rotating every 2. So our first 2 should be on the top. Our second 2 should be on the bottom here. If I isolate this, so this one here was on the top. It had an ethyl that was coming out from the center. Same thing over here. This one is on the bottom. Its methyl is going away from the center. When I'm doing my rotations, I want to bring this orbital that has the electron toward the middle because I'm making a bond here. So if I rotate this counterclockwise, that'll push this electron towards the middle. This one also needs to go counterclockwise because we want that to go towards the middle. So when I do that, rotating counterclockwise here is going to push this up. Rotating counterclockwise here will push this down, up, down. These are going to end up as anti to each other. Giving us this product. Our second example, we've got something bigger. So let's do that in blue. This one's going in. It's going out. Methyl, ethyl, methyl here. All right, still using heat. We've got 4 double bonds, which means we are going to make an 8-membered ring as our end product. Push this one up, up, over, down here. Eight-membered ring should look something like a stop sign. Have a double bond here, methyl, double bond on the side with an ethyl, double bond at the bottom with this methyl. And now we got to decide what's happening with these 2 O's. So drawing this out. First orbital pair is on top. Second orbital pair, bottom. Next pair, top. Last pair, bottom here. Let's isolate just the 2 endpoints. So this one's going in. This one's going out. This is on top. This one's on bottom here. So on the right side, I got to rotate this counterclockwise to move it inward. This one also counterclockwise. When I rotate the one counterclockwise, this one gets pushed upward, and then so will this methyl here. So both getting pushed up, which means they're going to end up as syn to each other. Could also do this with the same opposite method. Either of them works. So this would be your product here. Let's do the last two are going to be with light. So we're going to be using almost the exact same thing. We're just switching our orbital patterns. Grab some paper. All right. So we're in light. We got to draw an orbital pattern. We have 1, 2, 3 double bonds, which means we're going to make a 6-membered ring. It's going to look something like this. So we're using our light pattern, which means we need 1 electron on the top here, a pair of 2 on bottom, a pair of 2 on the top. This got a little quenched. And then the last one can be on the bottom here. Let's see. So isolating the middles, or sorry, the 2 endpoints. This has got an ethyl. It's got a methyl. They're both going out. One's on top. This one's on bottom. Let's do some rotating. We can rotate this one counterclockwise. This one's going to get rotated also counterclockwise. It's going to push this up. This arrow is going down. Going to push this one down. They're going to end up anti to each other. Blue. Like so. Okay, last one. We've got a 4-membered ring with multiple substituents on it. We're using light. We are 2 double bonds, which means we're going to make a 4-membered ring. Got these 2 methyls on it. Let's draw out our orbitals. All right, first one on top, pair of 2 on bottom, last one on top here. So isolating these. They're both going to end up on top. All right. One on the right, I got to rotate counterclockwise. One on the left, I got to rotate clockwise. So when I do that, this arrow is pushing this one up, getting pushed down by this methyl, and then the ethyl gets pushed up. So the 2 ethyls are syn to each other. So I can start by drawing that. That's probably the easiest thing to do. And then putting the methyl on a dash. Okay. There are 2 more reactions that are in this chapter that I'm going to cover, and then that's going to be the end of the material for exam 2. So let's get to those. They're pretty straightforward. They go kind of quickly. First one is called the Cope rearrangement. And the way we recognize these is that these are not going to be conjugated like normal. We've pretty much always had another double bond here, which would make this a fully conjugated system. These two are separated. What happens is kind of the same thing that's been happening. So these electrons will get pushed up. These ones will get pushed over. These ones will get pushed down. We're going to make, it's not going to be a ring. So we've broken this bond. We made a new one here. It should look something like so made a bond there, shifted this one over, shifted this one down, and we can get this. The reason why this occurs is because there's only one substituent here on our double bond versus this has 2 substituents. And because of that, this is more stable, which is what drives this reaction. If we had just this, where I don't have those 2 methyl groups on here, if I try to do this rearrangement, I started with 1 substituent, I ended with 1 substituent. So this is in fact, there's no gain in energy here. So because of that, this reaction won't actually happen. There's no energetic gain. There's no reason to do it. Okay, so that is the Cope rearrangement. It's driven by stability. The last one is the Claisen rearrangement, which is also driven by stability. It just involves an oxygen. This is our Claisen. This is going to be almost the exact same concept. We're just going to throw an oxygen here. Carbonyls are more stable than just double bonds. And because of that, a carbonyl can drive this reaction forward. So if I throw in heat with this, I'm going to check that in a second. This should get kicked up. This one will get kicked over. This one will get kicked down. So we broke the bond there, made the bond there. And should get something that looks like this. So as I said, carbonyls are more stable than just a regular double bond, so that's enough to drive these reactions forward. Someone in the chat asked if I messed up the pattern. Oh, in this last example, it still was one pair of two, one here. Oops. Maybe I said it wrong out loud, but that's probably what I wrote. So this is the light pattern where you have like one, as many pairs of two as you can have, and then a one, which is what we did here. We had one on top, a pair of two, and then one again on top. Okay. So those are all of the reactions that's going to be on exam 2. Let's talk about some synthesis problems. So I'm going to go through 2 of them. I'm going to give you 3 of them to do. I'll post a bunch more of them tonight. Let's start with A1 from chapter 13. All right. So if I look at this, and hopefully the more of these you do, you'll make the same kind of correlations. I got 1, 2, 3, 4, and a bromine. That's probably going to correlate to this 1, 2, 3, 4, and an oxygen. And on the other side, I've got this. This with this like double branch point and some sort of oxygen type thing, 9 times out of 10 is going to correlate to this epoxide. So depending on how we open it, we can get either this structure or the opposite structure, and I'll kind of go over that in a second. But if I take a look at this epoxide, and I think if I can open it with a nucleophile, if I do it in acidic conditions, I could make this, and then I would just need to oxidize this with something like PCC. So that's kind of our basis for this reaction. Taking a look at our starter material, we need an oxygen. We don't really want a bromine here. It's a primary position, so you can actually just do the SN2, which is nice if you throw an NaOH. You can make a primary alcohol. Technically, you could have eliminated and done some sort of BH3THF thing, but that's more complicated, and one step is always easier. From this point, we need to open the epoxide, and that is where you're going to have to make a choice. There's 2 different possibilities for epoxide openings. Especially with alcohols. First option would be to throw an H+ and our epoxide. So H+ is going to make you open on your more substituted center. We would get this alcohol as a review. We could also throw in, I'll do it in a different color, NaOH to get the O-, like NaO-, and then our epoxide. if we did that, we'd open on our less substituted position. So that would give us instead this epoxide opening. Looking at what we have, the oxygen is attached to this more substituted center like so, which means we're going to have to use the protic solution as opposed to the aprotic solution to do this opening. So let's throw in H plus our epoxide. We can get the majority of our molecule. And then from here to get to our final product, we just need to oxidize this. So doing a single oxidation with PCC can get us to our final product. So that's an example of a chapter 13 synthesis. I'm going to do a chapter 16 one, which uses a Diels-Alder. Oh, okay. Okay. So I'm going to give you a 5-membered ring. And I'm going to give you the stipulation this has to be your only carbon source. So when you're doing these Diels-Alder ones, the best thing to do is to kind of start by breaking your Diels-Alder in half. If you think of a normal Diels-Alder reaction, I've always got like when you're making that 6-membered ring and trying to break it, it would always break. So you get some portion of diene, some portion of dienophile. If I know I have a 5-membered ring as my only carbon source, that means I'm looking for 5-membered rings. I've got a 5-membered ring here. I've got a 5-membered ring here. That's probably the two things I'm bringing together to do this. If I ignore the chlorines and just think about how I would put this together, I probably want these two. This one's gonna be my diene, this one's gonna be my dienophile. I'll make it with a double bond and then I'll probably add Cl2 or something to add the chlorines on there. So let's take a look at how we're going to turn this into one of these two. And the more you do these, the more you realize you're kind of always doing the same thing. So this one is going to be easier to make. And then from this one, we can make our diene. So I get nothing on my double bond or nothing on my carbon right now. So I need to do a radical reaction, either Br2 or Cl2. And light will let me brominate. I'm going to throw a bromine here. Doesn't matter. This is an entirely symmetrical molecule. From this point, I can eliminate it with a base. And I've made one of the two things I'm going to need. So that's good. Let's make the other one. If I want to make 2 double bonds, I can throw in Br2 or Cl2. And a large base. Can get me to here. I've now made both components I need for this reaction. So from here, plus, oops, the dienophile we made over here can go to the vast majority of my skeleton. And now we just need to dichlorinate, so adding in Cl2. Let us add 2 chlorines anti across that bond. So if we're doing these Diels-Alder ones, oftentimes we're kind of doing the exact same reactions to make our diene and our dienophile, putting them together and then doing one other thing. I'm going to give you guys 3. Man, I want to go quick for this one. 3 different problems here. We are going to go through the first one, and then the other 2 we'll do on Monday. So as a hint for this first one, you need some sort of protecting group to do this reaction. For this one, you don't necessarily need a to use this as your only carbon source, but for this bottom one, I'm going to have you make both the diene and the dienophile out of that cyclohexane. So take about 10 minutes to go through these. Actually, someone asked me if I can talk through the last 2 steps again. On the previous example, so let's do that quickly. So the last step, or second to last step, was a Diels-Alder. So if I do a Diels-Alder between this diene and this dienophile here, I will make this 5-member bridgehead, this bicyclic system where this is kind of pointing downward, and that is the product from the Diels-Alder. If I add Cl2, I just have this one double bond here. So just like over here, we added Br2, it had anti across the double bond. We're doing the same thing, we just have a much larger molecule. So that gives us a Cl that's going up and a Cl that's going down here. On the page still. Does that help? Okay. So let's go. Ooh, yeah, about 10 minutes. I'll give you guys to work through these. And then we will do the first one together. The last 2 we'll do on Friday. All right, let's go through this first one. Let me redraw this. Okay, so taking a look at this, we've got what looks like an epoxide here. If we take a kind of a deeper dive into it, we're going to attack at this, which would be this center here. So we're going to be opening in the less substituted way. Nope, there's no stereochemistry on the second one. And I gave the hint that we're going to need a protecting group. And the reason behind that is going to really be if I just threw an NaOH here, made this the OH, and tried to attack our epoxide, I got an alcohol here, and I have an alcohol here. There's no reason this one wouldn't attack versus this one. So we need to kind of separate those two oxygens. So if I throw in my TMS chloride in the first step, I can now ignore this other oxygen. I don't have to worry about that opening the epoxide. So doing the same thing we just did, throwing in NaOH. Here, we've got an epoxide. We want to open it on our less substituted position, which means we are going to need basic conditions. Throwing in NaOH would make this into an O and A. And then our epoxide, we can open it on that less substituted position. So we would get H here. The majority of our skeleton. Because these are both ethyls here, I can do this part in one step. Well, two steps. So if I take off my protecting group with TBAF, ooh, one carbon short. From this point, if I want to add ethyls to both of these, I'm just doing our Williamson ether synthesis. So throwing in, we'll do it in excess because we're doing it twice, NaH to make these O minuses, and then excess ethyl iodide lets us do the SN2 to make ethers here. All right, that is all I've got for today. On Friday, we will go over those last two questions. We're going to do some NMRs. And then on Monday, we're going to go through the practice exams, which is going to be a little bit of a mess because some of it's going to be things, everything we crossed out from exam 1 is now on this one. And there'll be some new things to cross out from practice exam 2. Would I put those last two questions up? Yep. So I can throw them up right now. So I will see you guys on Friday. All right, looks like we're good.